Okay, let's just dive right into this explainer and discover how the very screen you're looking at right now, the device in your hand, and honestly the internet itself, are powered by what is arguably the 19th century's most monumental discovery. I mean, we're talking about life-saving medical technology, deep space communication, and literally the lights in your room. All of this modern magic really just boils down to four incredibly elegant mathematical statements known as Maxwell's equations. But the story behind them, it is an absolute thriller of human curiosity. It spans decades, completely defies social class, and it changed our conception of reality forever. Picture this. On the wall of Albert Einstein's office hung three portraits: Isaac Newton, Michael Faraday, and James Clerk Maxwell. Well, when someone actually asked Einstein if he stood on the shoulders of Isaac Newton, Einstein gave this incredibly surprising answer. He said, "No, I stood on the shoulders of Maxwell." He even wrote that the greatest change in our conception of reality since Newton was brought about by these exact discoveries. And you have to admit, that is a massive endorsement from the most famous physicist of the 20th century. Part 1. The equations that built today, tracing the legacy of modern technology. So to really understand how we got everything from our modern electrical power grids to wireless communication, we have to look at how scientific discovery actually happens. It's almost never isolated, right? It's this continuous relay race of brilliant minds passing the baton forward. And to understand James Clerk Maxwell's absolute genius, we have to start with the incredible, multi-generational relay race of human curiosity initiated by his forerunner. Because just as Einstein stood on the shoulders of Maxwell, Maxwell stood squarely on the shoulders of a man named Michael Faraday. You simply cannot have one without the other. Part 2. Faraday's self-taught genius. From bookbinding apprentice to scientific pioneer. Born just outside of London in 1791, Michael Faraday is the ultimate underdog story. He had almost no formal education, really just the bare rudiments of reading, writing, and arithmetic. He dropped out of school and started his working life as a poor bookbinding apprentice. But here's the thing, while binding those books, he acquired incredibly skillful hands and developed this obsessive habit of reading the very pages he was stitching together. He absolutely devoured an intellectual self-help book by Isaac Watts called The Improvement of the Mind, and that book taught him a vital lesson. Do not rush to general theories. Be guided strictly by observed facts. Basically, he was learning how to think like a scientist before he ever even stepped foot in a laboratory. Now, inspired by some local science lectures he somehow managed to attend, Faraday learned about Alessandro Volta's recently invented battery. This thing was taking the world by storm because it actually provided a continuous flow of electricity. So Faraday scrounged up his pennies just to recreate it. He stacked alternating copper and metal plates, placed brine-soaked cloth between each layer, and connected the ends with a wire. This was literally the first experiment he ever performed, and it was the exact moment he found his life's calling. He was totally hooked. From there, things moved incredibly fast. Thanks to this generous bookstore customer who bought him tickets, Faraday got to attend lectures by London's most prominent chemist, Sir Humphrey Davy. Faraday took meticulous notes, bound them into a beautiful little book, sent them to Davy, and, wouldn't you know it, landed a lucky job as his assistant. This put Faraday smack in the middle of a massive wave of rapid electrical discoveries that were just sweeping across Europe at the time. Part 3. The first electric motor, harnessing the circular force. In 1820, a Danish physicist named Ørsted proved that current moving down a wire actually produced a circular magnetic force around it. Well, Faraday, trusting only his own observed facts, reasoned that if a current creates a circular magnetic force, then a magnet should produce a continuous circular force on a current-carrying wire. So he built this ingenious setup. He fixed an iron bar magnet upright in a basin using hardened wax, and then filled the basin with mercury, which is a liquid metal that conducts electricity perfectly. He dangled a wire attached to a battery into the mercury, closing the circuit. Because the liquid kept the circuit unbroken while the wire moved, the magnetic force grabbed hold of that wire and literally spun it in continuous circles around the magnet. By harnessing that circular force, Faraday had created the world's very first electric motor. Fast forward a decade later, and he pushes the boundaries even further. He wrapped two sets of wire around a soft iron ring, and he discovered that when he switched the current on and off in the primary coil, the changing magnetism actually induced a brief pulse of electricity in the secondary coil. He realized something profound. Changing magnetism produces electricity. This is Faraday's law of induction. He eventually used this principle to make a continuous, direct current by rotating a metal disc between two magnets. He had just given the world the first dynamo. Guys, every single time you plug something into a wall outlet today, you are tapping into this exact discovery. Faraday envisioned a universe completely filled with these invisible, vibrating lines of force. He saw the world in these incredible visual ways. But here was the big problem. Because of his lack of formal education, he couldn't do the complex math to quantitatively prove his theories. So the broader scientific community remained super skeptical. To finish the race, the torch had to be passed to a man with an entirely opposite background, James Clerk Maxwell. Maxwell was wealthy, formally educated at Cambridge, a literal childhood math prodigy who published his first paper at 14, and an incredibly theoretical thinker. On paper, they were total opposites, yet scientifically, they were soulmates. Part 4. Maxwell translates the invisible, expressing lines of force through mathematics. While a lot of other scientists just dismissed Faraday's ideas of invisible force lines as totally wrong-headed, Maxwell was utterly convinced Faraday was right. He made it his singular, absolute mission to translate Faraday's brilliant visual intuitions into rigorous, undeniable mathematical language. He started by looking for a good analogy, and he looked at the steady flow of an incompressible fluid, like water. Think about it. Water flows outward from a source and weakens over a specific distance, which perfectly mirrors how electric and magnetic forces behave. By applying the math of fluid dynamics to Faraday's force lines, Maxwell successfully explained static fields and steady currents, which yielded the first two of his famous equations. But, it didn't explain changing currents. For that, he was going to need something entirely new. To explain changing currents, Maxwell proposed this absolutely mind-blowing mechanical model. Imagine space is just filled with tightly packed, microscopic cells that can rotate. As they spin, they create tiny vortexes, representing the magnetic field. But they needed something to stop them from rubbing together and creating friction, right? So Maxwell imagined tiny particles acting like ball bearings between the cells. And here was his real stroke of genius. What if these ball bearings were literal particles of electricity? When the electrical particles moved, they spun the magnetic cells. When the cells spun, they pushed the electrical particles. A change in one energy perfectly corresponded to a change in the other. And this wild visual model birthed a completely radical concept, the displacement current. Maxwell deduced that even in empty space, or inside a perfect insulator, these forces could interact. Electrical and magnetic fluctuations don't just happen everywhere instantly, they propagate. They bump into each other like elastic waves rippling through those invisible cells. This massive breakthrough is what gave us his final equations. Part 5. The speed of light, the ultimate plot twist in physics. So Maxwell realized that if these electromagnetic forces are propagating as waves through empty space, they must have a specific speed. Because scientists at the time already knew the experimental units of electromagnetic and electrostatic charges, Maxwell realized he could mathematically calculate exactly how fast these waves were traveling. Okay, prepare yourself for this because it is wild. When he ran the math on his displacement waves, taking the ratio of those known charges, the resulting number was roughly 300,000 kilometers per second. This was absolutely stunning. Why? Because that number exactly matched the already known measured speed of light. And that was definitely no coincidence. Basically, without even intending to, Maxwell had accidentally solved the greatest mystery of his era. He proved that light itself is just an electromagnetic wave. As he put it so beautifully, we can scarcely avoid the inference that light consists in the transverse undulations of the same medium. He literally united electricity, magnetism, and light into one single elegant mathematical framework. Because a poor, self-taught bookbinder and a privileged Scottish math prodigy decided to basically team up across time, combining brilliant visual intuition with rigorous, undeniable math, they literally lit up the modern world. Their work paved the way for absolutely everything we rely on today, which leaves us with a truly exciting thought to end on. If these brilliant minds could unlock the invisible forces of the 19th century just by trusting observed facts and relentlessly following their curiosity, what invisible mysteries are out there right now just waiting for someone like you to uncover?